One of the most interesting stories about the scientific method revolves around the evolution of the idea of continental drift into the theory of plate tectonics. We'll start with a little history of science lesson and then outline plate tectonic theory. Many people for many years had wondered, did Africa and South America once share a border? The shape, the puzzle fit, just looked too intriguing to ignore. A guy named Alfred Wegener first proposed an idea called continental drift. He was a German geologist, lived from 1880 to 1930, and he looked at that and decided that perhaps he would look for evidence that maybe they were once connected. What he used as evidence? Similar fossils in South America and in Africa. Similar mountain ranges that if you put the two continents together would be continuous. Climate indicators, things that showed that pieces of South America and Africa that lined up together had a similar climate sometime in the geologic past. So let's look at those one at a time. We'll start with fossil evidence. There are creatures that are land creatures that exist in swaths of South America and Africa. Again, freshwater mesosauruses that exist in southern parts of South America and Africa. Plant fossils that cross the lines between South America, Africa, India, Antarctica, and Australia. All of these things are things that cannot easily cross oceans, and they are of the same age and in the same kinds of rocks across multiple continents. So they seem to indicate that these continents were once in one piece. There's also glacial evidence. There's evidence of a very large glacier that is in all of these places and only works if you put it all together and form one large glacial mass that centered on Antarctica and covered South America, Africa, India, and Australia. And so Wegener was left with a question. If these things were once together, how did they move? And this is where he ran into a little bit of problem. His answer was centrifugal force. And centrifugal force, unfortunately, isn't a very good answer for how these continents might have moved. In 1912, he presented to the world scientific stage this idea that the continents were once together and that the movement of the Earth, the spinning of the Earth, caused them to move apart by centrifugal force. What do you think? Can it work? Well, actually, physics got in the way. And it didn't take the physicists very long to prove that centrifugal force just wasn't going to move continents. And so Wegener was dismissed and his ideas put aside, even though they were scientifically, geologically very sound, geologically well-reasoned. So where do we go from there? Well, Arthur Holmes was a British geologist who was a very strong supporter of the idea of continental drift. He recognized the good geoscience reasoning that Wegener used, and he suggested that perhaps mantle convection might be involved in moving of continents. It turns out that he was right, but he didn't have any evidence to support his convection theory, and so he couldn't move it forward very quickly. So enter World War II. Now you're probably wondering why we suddenly switched to war. As it happens, war often pushes the frontiers of science and technology forward, and in this case, in our plate tectonic story, there are two important scientific advancements that were made during World War II. First, this picture shows a worldwide seismic network. In order to monitor whether enemies were secretly testing bombs, the Allies put seismometers all over the world, on every continent and on remote islands, because a bomb, of course, will shake the ground just like an earthquake will. They may have discovered bomb testing, I'm not really sure, but they did discover a whole lot of earthquakes that are too small to notice, and they weren't randomly distributed either, but they were in very narrow and specific zones all around the Earth. Now, you might wonder, how can a person tell the difference between a bomb and an earthquake on a seismograph? Well, armies are very well regimented, and bomb tests happen exactly on the hour. Earthquakes don't. They were also looking for where German submarines might hide, and in order to search for what might be happening on the ocean floor, they began to do bathymetric studies, that is, the studies of depth from the ocean surface down to the ocean floor. It had originally been thought that the oceans were just flat, but as they started to gather bathymetric data during World War I and World War II, they discovered these vast ocean underwater mountain ranges that they didn't know existed. And these vast mountain ranges, as we know now, are mid-ocean ridges. The scientists didn't know what they were then, but they were very interested. So, at the end of the World War, these data, all of which were classified because they were all gathered by Navy and Army specialists, the data were declassified and the scientists got their hands on them. And this is where Harry Hess comes in. Hess was an American geologist. He died actually in 1969, but he was also a rear admiral in the Navy during World War II. So he had a little bit of a head start. He knew about these mountain ranges on the ocean floor before the data were declassified. When they were, he went to work with his proposal of seafloor spreading. He proposed that these mountain ranges were volcanic mountains and that lava was continuously erupting at the center of these ridges, creating new land and moving the older land further and further apart. So the seafloor, therefore, must be spreading. So, do you think he's right? Well, this is where the scientific method comes in. If Hess is right, well, you have a theory, so we need to come up with a testable hypothesis. If he's right, what would be a decent testable hypothesis? Well, we should be able to see that the ocean floor is younger in the middle and older on the edges, right? Because new crust is being, it's proposed that new crust is being formed always at the mountain ridges, and that it's pushing apart at all times. So A, we should be able to see younger ocean floor in the middle. And do we? Sure, that's easy. The ocean floor age is, in fact, a very easy match to the prediction that seafloor spreading makes. Young rock at the ocean ridges and older rock at the edges of ocean basins. We looked last time at the magnetic field, and we talked about the fact that there are magnetic field reversals. A couple of British geophysicists named Vine and Matthews knew about the magnetic reversals, and they realized that the magnetic reversals could support Hess's seafloor spreading hypothesis. If his seafloor spreading hypothesis is correct, then the magnetic reversals recorded on the ocean floor should be symmetrical from the ridge out to the edges. And sure enough, the magnetic anomalies are in fact symmetrical from the ridge out to the edges, and so these magnetic reversals also support the seafloor spreading hypothesis. So the pieces come together. Wegener proposed continental drift, but he couldn't explain how it happened. Holmes suggested convection below the crust could make the continents move, but he didn't have evidence for that. Hess came up with the idea of seafloor spreading, which could be tested. Dating proved that the ocean floor was indeed younger at the ridges and older at the edges, and the magnetic field reversals supported that hypothesis again. And that provided evidence that mantle convection is in fact an explanation for continental drift. So the full theory was articulated just a year before Hess died, and somewhere, I'm sure, Wegener and Holmes raised a toast.